Today, we are going to talk about conservation of mass. Conservation of mass is the key to tracking flowing fluid. It means that how much enters and leaves the control volume that we define. Um, so, the amount of mass in a system is constant. We talked about the system in the previous chapter, and we said that if I draw a system right here, the system is defined as a collection of unchanging contents. What I meant is that system includes all of the fluid we ever want to care about. So in the other one, it should never change with time, right? Because we've already defined our fluid to find our system to include all of the fluid that we wanted. So it means the amount of mass in a system is constant, right? This is why the time rate of change of the system mass is equal to 0. This is why we say that the mass is conserved, um, which we also call this principle as a conservation of mass or continuity. So the rate of the change of the mass system is 0, so also this one is equal to 0. And now if I apply the Reynolds Transfer theorem, and with B equal to mass and B equal to 1, as we talked about it on the last video, that how we can use Reynolds transfer theorem to keep track of something called B, right? Which we don't really know what is it. I mean, what is the B is. So I'm going to show you a review about the previous chapter. Let me just bring up. Okay, this is the note that we have, right? And if I go down to the Reynolds transport theorem, so we say that B right here, B right here is equal to BM, right? And then if we go down, this is another formula that we have, right? This is how we write down. Let me just copy this one and bring it to this node, right? Right, this is how we write it down. And then if also I go there and bring the other one, so let's find the formula. Yes, it's right here. So by comparing, by using the Reynolds transport theorem, so we can just, instead of B here, I can write down, because we are using mass, right? So M of the system, and then we have the rest, and instead of B, we say that there's a table that I provided in the previous chapter. If we use mass as B, B is gonna be 1, right? So then this is why here we don't have B. and just right here it's 1 for now. So B, we know that B is if for example let's say we don't know what is B, so but we know that B is per unit mass. So whatever it is, and the way we keep track of it is we say that the rate of change of B in our system is equal to the rate change of B in our CV, within our CV, plus the rate of change of B, that or the rate at which B crosses our CV boundary. So now if we set B equal to mass, this is what we have here right now, this formula. And if I want to just say what is the meaning of it, so this one means the rate of change of mass within control volume, and this is the net flow rate of mass across the control volume. So which all of them is equal to 0. So we already talked about the steady flow, but again, if we have flow which is in a steady, we said that all field properties at any specified point, including density, remain constant with time, right? So the time rate of change of mass also of mass of the contents of the control volume is going to be 0 if the flow is a steady state. Also, this is the formula that we have for flow rate, and this is I'm using again the Reynolds transfer theorem, and let me see, where is it? It's yeah, it's right here. So if we use the Reynolds transfer theorem, which is here, just ignore this part. So this is how we also get this formula. So in B is 1, we already know that because we use the big B as our mass. This is how B is going to be 1. So from here we have the rate of the rho v, which is our velocity, dot n times dA is equal to our m dot out minus our m dot in. This sign is coming from that we also showed in the previous chapter, so I'm not going to go through the chapter again. You need to review that. But the thing is that I show you, if we have the velocity going in, we have a negative sign, and if the velocity is coming out, we have a positive sign, and it's because of the nature of the dot product, right? So let me just write down 2 points here because it's important. So what I said is that the sign of the dot product v dot n is positive for flow out of the control volume, and also the sign of the dot product of v times v dot n is negative for flow into the control volume. And this formula right here is the mass flow rate that goes through a section of control surface that has a area of A, and so the unit gonna be kilogram per second, and then Q is the volume flow rate, which is equal to A times V, and the unit is going to be m cubic per second. And in this formula, this V is the average fluid velocity, and also this rho is the average values of fluid density. So, and for the incompressible flow, this is uniformly distributed over area A. So it means that it is appropriate to use this equation right here when the average value of the component of velocity normal to the section area involved, and this is the definition of the average velocity right here. And also we don't use, we don't need to use this symbol for average velocity. We can use that one, and it means that so in general this is the equation of mass flow rate, but with some conditions that I just mentioned, we can use the above equation. By above equation I mean this one. So but just for a side note, I'm going to say that for most of the problems we give you most, not all of the problems, but you won't have to do the integral, so we can easily use this formula. But I'm saying that for most of the problem, not all of the problems. So in the next video I'm going to talk about control volumes and solving some exercises.